All right. Thank you everyone for coming. It's my great pleasure to introduce my good friend Harry Crane, who comes to us from Rutgers University. He's associate professor and co-director of the graduate program at Rutgers in statistics and biostatistics. We're glad to have Harry here today. Thank you very much. Okay. Oh, sorry. He's going to be talking about coherence in statistical modeling of networks.
Well, thank you. Yeah, thanks to Eddie for arranging the visit. It's been a great visit so far. Thanks to everybody for coming, and thanks especially to Carrie for inviting me, although he's not here, unfortunately. I will maybe mention Carrie's name a few times throughout these slides because I prepared this talk specifically for Carrie. I've never given this talk before, but when we met in Cambridge last year, he brought some of these ideas, these things up, and he, as I understood it, he wanted me to talk about this, so I chose to talk about it. But I'm happy to do that because these are some things that have been on my mind for a while now, and there's still ideas that are developing in my mind. So actually, one of the reasons I was hoping Carrie would be here is to maybe call into question some of the things I'm about to say and maybe criticize some of the things I'm about to say. So if somebody would like to take his spot, that would be great.
Impossible.
But he did already send some criticisms by email, so maybe when they become relevant. Okay, so I'm talking about something that I'm calling coherence in statistical modeling, which I'll define in just a bit. I hope you'll agree it's a relatively basic idea, but not everybody necessarily thinks that way. So thinks that it is. So, but the idea is that, and it's not specific to networks at all. It has to do with statistical inference and statistical modeling in general. So if we're trying to, the basic idea is that a statistical model should be coherent in the sense that inferences from it make sense. And I want to try to make that idea precise as much as I can. And I'm going to apply this idea, or at least discuss its implications specifically in the context of networks, because I think that at least in some more modern applications, this is where some of these ideas are made. It's maybe this concept of coherence, I think, is something that appears in any kind of statistical setting, even very classical statistics. But it's in classical statistics, it's kind of unspoken because it's kind of by convention that it's already built in, and in maybe more modern, more complex applications, it's not the case. So to start off with a discussion of, well, first of all, what is a statistical model? And if I go to these are some classic textbooks on statistics, Bayesian statistics, theoretical statistics, and even a more recent book on the analysis of network data, all define a model to be something like this. A model is a statistical model is a set of probability distributions on the sample space. And I'm particularly interested in understanding what this definition means, or what its implications, or really its drawbacks are with respect to this well-known quote by George Box. And I don't want to, so I'm not necessarily going to call into question this quote, but I do call into question the citation of this quote. So oftentimes I've given the talks about modeling in networks, or I've asked people questions about models that they use for network data. And well, until very recently, there were very few models, and still are very few models available for networks. But 5 years ago, there were even fewer, and so there was very little to choose from. And so it's almost by default that whatever model is being applied in a given situation is somehow inadequate, or can somehow be criticized if you look hard enough. Usually, you don't have to look very hard. But in defense of using a model which is somehow clearly inadequate, many people have just cited to me and say, well, all models are wrong. So, in other words, I can use whatever I want as long as it's useful for my purposes. So the question is, well, what does it mean for a model to actually be useful? You know, there must be some standard, or at least in my mind, there has to be some standard that we go by. So I want to try to make sense of these first two, what I said on these first two slides, and how it might be brought into, how it might affect things like network modeling or analysis of network data. Okay, and so let me start with my conclusions, so that just to be nice to those of you who are already starting to maybe zone out on some of these things. What I want to say is three basic.
It's too late for me.
What I want to say is I want to make three basic points, and actually, I think they're kind of very elementary in some way, but getting to them requires kind of revisiting some basic principles of statistics. So I will try to convince you that a statistical model is something more than just a set of distributions. So there is a set of distributions involved in modeling which describes the data, but there is more to it. What makes a model statistical is that it can somehow be used for statistical purposes. And so there's some additional context that I think statisticians know this in their heart, right? And that applied statisticians take this context into account when they actually apply statistics. But where I think this additional information is lacking sometimes is in the development of the theory of the statistics, where maybe the context in which this theory might be applied isn't always taken into account. And the reason this is important is because with this additional structure that we put on these models, we can maybe come to some conclusion as to what makes a model useful. And my take on what will make something useful, at least the first step towards being useful, is that the model makes sense, or at least that inferences from it make sense, in the sense that the inferences can be interpreted within a single context. So I'll make this a bit more concrete as we move forward. But then I want to talk finally, in the second half, I'll talk about what are the implications of this towards network analysis or network modeling. And the key issue there is that, so the context that I'll focus on for network analysis is specifically assuming that we're analyzing networks that have somehow been sampled from a larger population network. And as it stands right now, there's very little attention, there has been very little attention in the mathematical statistics literature at all on the effects of sampling in network inference. But those that have paid attention to sampling effects have almost always focused on specific types of, very kind of stylized sampling schemes that have to do with picking vertices at random or something like that, which is not typically how most of these real-world networks are observed. Okay. So just to start off, I want to address these first two statements, and in order to make sense of the model, the notion of usefulness, I first have to describe, well, what I'm actually using the model for. And there are a lot of ways to potentially use a model. The exploratory data analysis or some descriptive statistics is maybe the most basic way to do it. And in that case, actually, a lot of what I say, if all we were interested in doing was exploratory data analysis, a lot of what I say is not really relevant. What I'm mostly going to be focused on here is specifying models in which we want to do, for the purpose of doing inference outside of the sample, or whether it's prediction or somehow using the estimates we get from the data that we have to say something beyond the sample. Okay. And I ask this, again, this is geared more towards Carey, which is that I know that he works a lot in asymptotics, and I don't, but I'm wondering how some of the things that I say with respect to this would affect maybe how we do asymptotics in the field of, in the study of networks. So the first thing I want to get to is this idea of a statistical model being a set of distributions, and start with one of the most basic classical setting that we could think of, which is that the model we specify a model as some potentially infinite sequence of IID random variables from some normal distribution with unknown mean. Okay. So this is a standard way of specifying a model that you'll see in articles in the Annals of Statistics, things like this. And it's kind of conventional. It's now implicit in the conventions that have been built up over the course of 50, 60 or longer, 50, 60 years or longer, that when I say this, it's known what I mean by this, in the sense that, well, what I really mean is that I'm going to observe data of some finite size, so some sequence of finite length. Well, the model as a set of distributions is just this set of normal distributions. And I want to estimate, so this is the parameter that I'm interested in doing inference for. And what allows me to do inference for this population parameter based on just a sample is that I'm implicitly, kind of, in saying this, I'm implicitly making the assumption that, well, it's not just that this infinite sequence is IID, but I'm actually assuming that for any finite sequence I observe is also IID. And that's what provides the connection between the sample and the population that allows me to connect the estimate to the estimate from a sample to the population parameter. But that relationship is implicit in the specification of the model. And it doesn't cause any issues in this situation because at this point it's accepted convention as to what I mean. But as we'll see later on, and for those of you who work in maybe in networks, you're probably already aware of this, that while it's conventional in classical statistics to leave this implicit, in more modern applications, this could lead to confusion due to the ambiguity that it introduces into the model. Okay, so in particular, if I'm assuming, so if I leave the relationship between the inferential universe, this is the population that I'm interested in doing inference about, and the observed data, which is my sample, then it's not clear how to, well, it's not actually clear how to do inference, or how the inferences are to be interpreted. And so, and even still in a very classical or very simple setting, we can illustrate the effect of this context in another example from IID sequence data. So if I assume I have an IID sequence of household sizes, so I assume so the size of the household is the number of residents, number of people who live in the house, and I just assume household sizes follow a Poisson distribution, essentially. And I want to do inference about the average household size in the population based on doing some kind of sample from the population. And there's a few ways that I could do this. One way is I could sample households uniformly at random. And if I were to do that, then since the population was IID from the Poisson, the sample was also IID from the same distribution. And so I have a very clear relationship between the sample and population. Or alternatively, I could sample individuals in the population and ask them the size of their house, but now a house with 4 people is 4 times as likely to be chosen to appear in the sample than a house with only 1 person living in it. And so I'm choosing from a size bias distribution. And so the point of this is that in both cases, the model that I've specified, if we think of it this way, the model on the population, on the sample space that I'm studying, the set of distributions is the same, but obviously the way that I would do inference is different. So there must be more. There must be more to a model than just this set of distribution. This set of distributions on the population. Okay. And so I want to try to make this as precise as possible. Or at least I want to try to now bring myself into a situation where I can make this idea precise. So there's many different, and this is what I'm introducing as this idea of context, which is there are many contexts where the context is understood as just the circumstances under which the data is being analyzed. Okay. So there are many contexts in which actually affect statistical analysis. Of course, there are kind of practical and ambiguous issues with context, things like legal issues or ethical constraints that are very hard to pin down what their effect on the analysis might be. But there are also some more maybe more distilled or more more distilled notions of context, such as sampling and the actual generating process that are more amenable to being incorporated into a formal analysis. And my claim is that nothing that I've said is actually surprising to any statistician, so that applied statisticians for sure already know that the circumstances affect their analysis, and somehow that is accounted for intuitively through the expertise of the scientist or the applied statistician. I would also say that mathematical statisticians know this as well, but mathematical statisticians don't usually analyze data. And so when they establish the mathematics, they often, it's much more convenient to just ignore this, and oftentimes. Yes?
Can I just, the second bullet, when you say they account for it informally or intuitively, isn't it also the case that there's a lot of applied statisticians that have formal methods for accounting for it? So for example, in bias sampling, there's adjustment for sampling.
Yeah, sure.
Okay,
yeah, so for example, I mean, in this case right here, there's obviously a way of accounting for it. Yeah, absolutely.
So it's not just informal, I guess.
Okay, I mean, I'm not trying to say that they do it, that it's bad. So to me, informal is not bad.
No, I'm just wondering if you would call that formal or informal, because I think of it as formal.
No, I would agree. But I guess what the point is, though, is that there's obviously something additional to the set of just some set of distributions that's being taken into account. So that's what I'm maybe more to the point of what I'm trying to say. Okay, and so what I'm going to do is I'm going to hone in on just a specific type of context, which is assuming that we have data and that's somehow sampled, and I want to see how that actually could be incorporated into the model in a way that maybe allows for this to be addressed inside of a formal theory. Yeah.
So when you speak of lab experimental conditions, are you referring to the fact that your model itself could be wrong because you have noise and you're not taking into that probability distribution, or are you referring to something else which is different from the model? So I'm trying to figure out what else other than the sampling scheme are you referring to?
I mean, so these are, so I don't have anything specific in mind.
Okay.
So I don't want this to be taken too literally. I mean, I'm sure that, the point is just that there are circumstances that affect data, that affect data. To every extent possible, they should be accounted for. Whether they can be or not, in a formal theoretical sense, is part of the challenge. But I guess the one thing that you asked is that, am I talking about the model being wrong? Okay, so that's something I didn't say when I brought up the original Box quote, which is, he says, all models are wrong, but some are useful. So, like I said, I'm not necessarily taking issue with the quote. I think I know what he means, but I actually don't. I don't think that the statement as stated actually means anything. So, I mean, what does it actually mean for a model to be wrong? Especially if they're all wrong. I mean, it's not clear what that actually means. But I think that's not the important part. The important part is making sense of what it means for a model to be useful.
Are you sure that when he said that, he was expecting that people would be repeating it for years?
Yeah, so that's why I don't want to criticize Box, right? That's especially that picture. He looks like such a nice guy. Okay, so what a statistical model is in this way of thinking about things is that there's a descriptive component to the data. So there is the part that actually describes whether it's the uncertainty or the variability in the data, and that's through the set of candidate distributions, and that's the traditional set of, traditional set that models are, typically defined as. And then there's this additional context under which the data is observed, and it's through this context that provides the relationship among different sets. So the way that these different sets come into play is that if I think of this as a population model, that for each possible sample size, the population model plus the context is going to induce a family of models for the data of size n. Okay, now that's one way of coming about this. The other way would be, and another way of looking at this is to specify outright the model, the set of candidate distributions that I'm going to fit to data of size n, the set of candidate distributions I'm going to specify to data of size n plus 1, and so on. So that's another way of doing this, and you would get a family of sets, these MNs that I'm writing. And then the question is whether or not, so the modeling part, or the descriptive part, is just this set of distributions. But what actually makes the model statistical, I would argue, is that it can be used for statistical purposes. And in my case, that's for doing inference outside of the sample. And in order to make that, make the model statistical, there has to be a context under which the inference. The model has to take into account the context under which the inference is being performed. Okay, so the picture of what I'll talk about with respect to networks is given here. So I'm assuming I have a population network that's modeled by some set of distributions. I assume I'm taking a sample to observe. So what I actually observe is this, and there's a model that's induced on this sample network through the context and through the sampling context that I'll try to make precise. In the examples we've already discussed, the model, if we were thinking about IID sequences, so the model was a set of normal distributions. When I observed the finite sequence of length n, the induced models, the implicitly specified, were just these n-fold product measures. And in the case of household sizes, because of how I did the sampling, the sample models were induced as size-biased, or models from the size-biased distribution. Okay. So that's my definition of what a statistical model is. And now getting to the part of actually using the model or making it useful. This is where this idea of coherence comes into play. In that, so nothing here is, so everything here is very generic. So I'm not, I'm not wedded to any specific, any particular way of doing estimation or inference. So I'm just assuming that given data of a certain size, we estimate some optimal candidate distribution according to some criteria. And then once we have that estimate, we want to do inference for what the corresponding optimal candidate distribution is for the population parameter. And this is done by interpreting our estimate in the appropriate context. So the way that this is done in classical IID modeling is that we estimate a parameter mu from the sample, and then we use the same estimate to estimate the population parameter. But in principle, these are actually different parameters, but then it's a matter of transferring the meaning from one to the other through this relationship, through the sampling relationship. Depending how these distributions here are parameterized, there may be a one-to-one, there may be a direct identity relationship, or there might be an offset by one. But in either case, we actually can explicitly describe what the relationship is, and so we can do inference from the sample to the population parameter just by this transformation, just by a simple transformation. Okay. So now what I want to do is I want to try to get so in the way that I've described this model of household sizes by sampling individuals, we've accounted for the sampling in this estimate, in this transformation of the estimator. But I want to find, what I want to do is I want to describe a way to incorporate this into the model formally, so that if we were to develop methods, formal methods, or formal inference results for inference procedures, that it can all be incorporated kind of in a more general context, more general setting. Okay, so here I am talking specifically about sequence data. Okay, so I have real valued sequences of length n, and the sampling. So the sampling scheme I'm going to assume here is just basic projection sampling, and this is just to illustrate. This is to illustrate some of the notation that I use, which I think is non-standard notation. But so selection sampling is just projection from the first projection onto the first m coordinates. I'll call this selection sampling, and that all it means is that I have a sequence of length n, and then I sample by selecting the first m labels. For any distribution, this sampling will induce a distribution on sequences of length m. And I write this to be the induced distribution. So that would normally be written this way. But there's a reason why I write it this way, and you'll see in a minute. But what this means is that I first generate something randomly according to f, and then I sample from it according to this. Okay, so that's just the induced distribution. And from this, I get an induced model. If I were to have a set of distributions on sequences of length n, then I can get a model that's induced on sequences of length m by applying this sampling scheme to every candidate in my model. So the picture in the ordinary in the classical setting is that I assume that the population is an infinite sequence of IID sequence. So this is my population model, and the sample model is defined as IID sequences of length n. And the reason is because that's the induced distribution. If I project onto the first n coordinates of an IID sequence, then I end up with an IID sequence. Okay, so that's all very elementary in this particular case. But technically, that relationship established by the sampling scheme is necessary to justify the inferences going from observation to the sample to population. It's just that it would be considered a bit pedantic to do that, I think, in this setting in general. But the key point is that this sampling mechanism is almost always left out of model specification, because I think it's kind of we're kind of used to being in situations where it's obvious what it means. But my argument in networks, for sure, this is not to be taken for granted. Okay, and we'll see several examples coming up. Okay. More generally, and so this, I should say, this selection sampling is very so. This is taken as the default sampling mechanism, but it's very unrealistic in many cases to think of this as an actual sampling mechanism. So in a lot of cases it might be that like in the household example, the way that I sampled the data actually depended on the data itself. So there was a dependence, and so if I wanted to maybe incorporate a more general kind of sampling, I'm going to define what I'm writing as psi sampling, which just means that psi is an injection, so it takes, so what it's going to do is it's going to pick out m of the coordinates, and what I do is I observe those m coordinates. Okay, so it's not just a strict projection onto the first m coordinates. And I'm going to let sigma, so this is a random sampling map, which is obtained by choosing a random psi and then just applying this operation. And the distribution of psi can actually depend on the data. Okay? And then the same notation carries through. This is going to induce models. This is going to induce a model for each finite sample size. And the idea behind coherence, and this is the definition, which is that if I have a model, a family of distributions, and a description of the sampling scheme that's in use for doing inference from this model, that this model is coherent if the induced models, for all finite sample sizes, the induced models agree with the specified models. Okay. And what the implication of this, which I'm going to show here, the implication of this is that under this condition, this model is somehow consistent with itself. There's no way to. So if this didn't hold, that if there were an inequality here, then the description of the data under the description of data of size m, if I were to assume that it were sampled from a sequence of length n, would be different than the actual specification that I've made implicitly in the model. Yes?
Can we just go back one slide? So the bold-faced X represents an infinite sequence.
Depends, if it's subscripted by n, then it's a sequence of length n.
Right, but the bold-faced X that you have
Yes,
that population,
yes.
that just represents an infinite sequence of real numbers, the way you're conceiving of it. So
These are real values, yeah.
So the xi's, the little xi's that are not bold are just real numbers.
Yes.
Okay, and then so the xn the bold xn that you've written is just a truncated.
Up here.
Part of it.
Or here,
Yeah,
yes,
yeah.
yes. This is given by this, yes.
Okay, so when you write s sub n comma natural number x, your
This is indexed by the natural numbers,
right?
and I'm just saying I'm truncating to the first n, little n, of this sequence in this case.
Okay, so the second thing, the second index in your Sm sub n communicates the domain from which you're then doing the truncation, right?
Yes,
Okay.
yes, yes.
No, probably we'll talk more about this, but it looks like a very strong condition. Why? I mean, if you allow for n equals infinity, why not just considering samples extracted from an infinite? Is it? Why do you need to have all this?
Right. Well, you could do that.
hierarchy?
No. Well, so this is you could specify this to be what you're. So if you just had it would only have one index here in your case, right? You could do that. I mean, I'm specifying in this particular case. This is what I've chosen. This is what I've said are all the possible ways that I could have sampled this. So that's what the condition would be. More generally, if you were only assuming that you were sampling from an infinite.
Yeah, you wouldn't have to require that the stepwise reduction is consistent, is coherent.
Not necessarily. Not if you don't want to. I mean, in some cases, so the reason I put it this way is that in some cases there might not even be this idea of there being an infinite object might not even make sense.
Right, you could be talking about finite population sampling, right?
Yes, you could.
This would cover that.
Yeah, exactly. So maybe the next slide will make this. So it is a strong condition, and that might be an objection to it. But how this